Okay, so now we are going to look at the same kind of thing we did in part one with lines in 2 space. Now we're going to look at lines in 3 space. So in 3 space we have vector and parametric equations that are going to look very, very similar to the ones that we just worked with, except we have a third component, which shouldn't come as a surprise. We can write vector parametric the same way. However, we can't do a scalar equation of a line in 3 space, and that's because a scalar equation is actually going to represent a plane, which we'll learn in the next lesson or two. So for us, we're going to look at vector parametric, and then there's another format called the symmetric equation of a line, and you'll see what that looks like as we work through our examples. All right, so this slide should look very, very similar to the one that I posted for the vector equation of a line in 2 space. We have our position vector. So that part hasn't changed. So we still need a position vector, also known as a point. And we still need our direction vector, which is the slope of our line. Slope is comparing rise over run. Direction vector is going to be comparing the x, the y, and the z. So if you'll notice the parametric equations, same exact setup, except now we also need to consider the z component. So in terms of the mechanics of the line in 3D, the exact same thing as the line in 2D when we're talking about the parametric and parametric and vector equations of a line. Now, the symmetric equations of a line in 3 space, we can get them from the parametric equations. So the parametric equation breaks it up into the x component, the y component, and the z component. You'll notice in each of the 3 components, we rearranged and isolated for t. So t, whether it's the x component, the y component, or the z component, it has to be the same value that we're working with. So since we know that t has the equal t has the equal t, we can set those 3 rearranged equations equal to each other. So this here, this is the symmetric equation. So this is what they will look like. Now, a couple little notes here. The direction vector, you've been taught never to leave negatives in the denominator. That's not true here. You have to leave negatives in the denominator because they represent your direction vector. You can't change the signs because then it ends up changing the values that we are going to be working with. The other thing that's important with symmetric equations, you need to have at least 2 parametric equations. So you're probably like, well, what does that mean? Well, if I have a vector that is 0, 0, 1 plus t -4, 0, 0. So if I create my parametric equations, I'm going to have x equals 0 minus 4t. I'm going to have y equals 0 plus 0t. And then z is going to be 1 plus 0t. So if I'm isolating this here, I'm going to have x divided by -4 is going to equal, I can't equal it to the y value over here. And that's because when I rearrange, I'm going to have y over 0 equals t. That can't happen. I'm going to have z minus 1 over 0. That can't happen. So if your direction vector has multiple 0 values, it doesn't work in terms of our equations. All right, so here's a typical question, just like any other example. So in A, you're being asked to write the vector equation of a line. So we need a position vector. I have 2 to choose from. I have A and I have B. What I need, though, is my direction vector. So my direction vector is the difference between those 2 points. So I have 3 subtract, I'm going to say that it's AB. So 3 take away 2 is 1. 6 subtract -1 is +7. And then -4 take away 5 is going to be -9. If you chose to do AB, you would have gotten -1, -7, +9. Same thing. Now that I've got that, R is equal to, you can pick A or B. I'm going to pick B this time. 3, 6, -4 plus T. Got to have that parameter in there because that gives me a set of points along the line. And then my direction vector is 1, 7, -9. Done. Now part B. So part B, I want the parametric equations. Okay, so x equals 3 plus t, y equals 6 plus 7t, and z equals -4 minus 9t. So this actually leads very nicely into part C, because part C wants the symmetric equations. So in C, I have x minus 3 divided by 1 equals t, y minus 6 divided by +7 equals t, and z plus 4 over -9 equals t. So now when I write the symmetric, I'm going to have x minus 3 equals y minus 6 over 7, which equals z plus 4 over -9. You'll notice I didn't write the 1 for the x. You can if you want to make it obvious what the direction vector is, but you don't have to. Now, part D. Determine if the point 0, -15, 9 lies on the line. The easiest way to do that is to sub into the symmetric equation. So I'll have 0 minus 3 equals -15 minus 6 over 7, which equals 9 plus 4 over -9. If the point is on the line, it's going to satisfy this equation. So I have -3 equals -15 minus 6 is -21, divided by 7 is -3, so it's looking good. But then I end up with 14 over -9. So therefore, no, the point is not on the line. Okay, now a normal, we talked about the word normal in the calculus component of the course. So normal is a line that's perpendicular to a line. So back in grade 9 and 10, and even at the beginning of the semester in calculus, if you know the slope of one line, you automatically know the slope of the other line. So that kind of applies a little bit here. If we have the direction vector for one line, in 2 space we can figure out the direction vector that's perpendicular in 2 space. Now if I have a line that is in 2 space, I'm just going to draw a random line here, right here. I'm going to put arrows because it is a line. There's an infinite number of lines that are perpendicular to it. So I can draw one here, I can draw one here, I can draw one here. They're all perpendicular. They're all the same vector. They're all parallel to each other. They're all collinear. They're all the same multiples. However, if I have a line in 3D, if I'm looking at this line, I can have a line that's perpendicular right here, but I can also have a line that's coming out right here that's perpendicular. Or we could have a line that is going down that is perpendicular. So there's not an infinite number. There's only, there's not an infinite number for the 3 space line in terms of the same vector. They're all different vectors, okay? Whereas in 2 space, they're all the same vector, whereas in 3 space, they're not the same vector. Okay, so determine the vector equation of each line. So what do we need? Always ask yourself these same questions. You need to know the direction vector. So we need m. And in this example, this is m. So I know that that's 3, -5, -9. So it's parallel to this line, so that's what I need. Then it's telling me that this is the x-intercept. So this would have the coordinate -10, 0, 0 in terms of a point. So that means the vector equation is r equals negative 10, 0, 0, plus t, 3, negative 5, negative 9. Done. Okay. This one here involves a little bit more work. So it says with the same z-intercepts as x, y, and z, given that first equation. You'll notice there's no position vector in this first equation right here. That means that the point 0, 0, 0 is on there. So the z-intercept. If I was asking you to figure out an x-intercept in grade 9, you substitute at y equals 0. We're going to do the same thing. So for the z-intercept, x equals 0 and y equals 0. Now for this first one, because this vector equation of this line right here, if I were to write that out a little bit differently, it's 0, 0, 0 plus t 4, negative 4, 1. Do I actually already know the x-intercept? The answer is yes, because this is my x-intercept. X, y, and z end up all being 0. So this is the x-intercept. The z-intercept I'm talking about is the same as this one. Now the x-intercept, so step 2. So we need the x-intercept. So I'm going to let y equals 0 and z equals 0 in the parametric equations. So first off, I'm going to write them. X equals 6 plus 3t, y equals 3 plus 6t, and z is going to equal negative 1 minus 2t. So I'm going to start by subbing 0 in for the y. So 0 equals 3 plus 6t. When I rearrange, I'm going to get negative 1 over 2 equals t. Same thing over here. I'm going to get negative 1 over 2 equals t. So I end up with the same t value. That means an intercept exists. Sometimes there are no intercepts. Lines in 3D do not have to have intercepts. So now I'm going to take that t and I'm going to sub it in. So I get x equals 6 plus 3 times negative 1/2. So x is going to have a value of 9 over 2. So that means that I have the point 9 over 2, 0, 0. Okay. So it's a point, so it's a round vector. So my goal is the vector equation of a line. So step 3, we need a direction vector. I have 2 points. I have 0, 0, 0, and I have 9 over 2, 0, and 0. So that means my direction vector is 9 over 2, 0, 0. So now when I write my equation, I can have r equals, I'm choosing to use the position vector 9 over 2. So it's perfectly fine that your direction vector and the position vector is the same value. Because if you were to graph this, you would see that you're just connecting it to the origin. Okay. So knowing how to find intercepts, process is pretty much the same thing. However, you have to use the parametric equations. All right, so our last example that we have here. So we have line 1, line 2, and line 3, and you're being asked, are they the same line? So the first thing we're going to look at is the direction vector of each one. Because if they're the same line, that's the first thing we need to look at. So they're all multiples of each other. So the direction vectors are all the same. So they're all parallel at the very least. Now we want to know if they're the same line or a unique line. So when I look at this first value right here, I'm going to take line 1. I'm going to sub the point from L1 into L2. So the point that I'm using is 11, negative 2, and 17. So that's the point from L1. And from L2, I'm going to use the parametric equations. So I have x equals negative 13 minus 3t, y equals 6 minus t, or sorry, it'll be plus t, and then z is going to equal negative 10 minus 4t. So if it's the same line, this point has to be on it. So I'm going to sub in the 11 where the x is. So I'm going to get 24 equals negative 3t, negative 8 equals t, negative 2 equals 6 plus t, negative 8 is equal to t. So far it's looking like it will be, but I still have to check that final component. So I get 27 over negative 4 equals t. So what that tells me is L1 and L2 are not the same. Okay, so same process. I'm going to sub the point from L1 into L3. So the parametric for L3 is negative 4 minus 6t. Y is 3 plus 2t. And z is negative 3 minus 8t. So the value of the point, the x value is 11. So I'm going to have 11 equals negative 4 minus 6t. So that'll be 15 over negative 6 equals t. That's negative 5 over 2 equals t. I'd have negative 2 equals 3 plus 2t. Negative 5 over 2 is equal to t. And then with z, I am going to use 17 equals negative 3 minus 8t. So 20 over negative 8 equals t. That's negative 5 over 2 is equal to t. So therefore, L1 and L3 are the same. Since we know that the point from L1 is not on L2, L2 and L3 cannot be the same either. Okay, so that sort of concludes the vector, parametric, and symmetric equations in 3D. The key thing is just recognizing that we have to include that z component and that there's no scalar equation of a line in 3D, only symmetric.